Okay, welcome back to Machine Learning Compilation. This is lecture 4. Thanks everyone for keeping with the status. Today we're going to talk about exciting topics. So in the last lecture, we talked about how do we build primitive tensor functions and different ways of transforming primitive tensor functions. In today's lecture, we're going to focus on how do we combine those primitive functions to really start doing end-to-end model execution. And as of last lectures, we are also going to start to do a hands-on examples on how we are going to do that. So today's lecture is also going to be notebook-based. To begin with, we can install some of the dependencies that help us to run through this lecture. I want us to recap a bit on the overall MLC process that was the main theme that we had in the last few lectures. Specifically, an MLC process can be viewed as a way for us to take a model in its development form on the left-hand side and trying to be able to transform it onto a deployment form on the right-hand side. Of course, depending on the specific MLC process, the development form and deployment form can differ. And a lot of the past lectures we have spent on how do we define, for example, a single tensor primitive functions. And today we are going to think about how do we really run model end-to-end. And again, throughout the lecture, let's keep the following question in mind about what are the possible abstractions that we can use to represent the tensor functions, and what are the possible transformations among the tensor functions. Okay. So in the past lecture, we have been focusing on this part. And today we're going to focus on more of this part of the execution, where how do we stitch each of the primitive functions together. Okay, so to do that, we will try to import some of the necessary dependencies and helper functions. Again, we're going to use TVM as an example for showing some of the concepts. Of course, the concepts we teach in this class generalizes beyond the TVM framework. So to begin with, we're going to import TVM, and we're also going to import IPython. One of the things that you might notice is that there are additional importations that are a bit slightly different from previous lecture. So first of all, we're going to introduce RELU, which is a high-level computational graph abstraction that help us do end-to-end executions. And then we also need to introduce this annotation feature that allows us to defer annotation parsing in TVMScript. So in order to run end-to-end model, of course, we want to have a real example, but the example also need to be self-contained so that we can really understand the details behind the scene. Remember, our goal is not only to be able to run the models, but also really understand what's happening behind the scene. So we're going to use a small data set called fashion MNIST. So in this piece of code simply downloads the fashion MNIST data from Torch Vision. And then we're going to load it in and load the first image onto that's randomly selected from dataset onto a Numpy array. And if you run this notebook multiple times, you might find that you will get different images each time you run a notebook. But that doesn't matter, because we are just going to randomly pick one example and build a model that runs on this example. Okay, so the download finishes. I'm going to plot the first image that we had in here. So this is the image, and in this particular case, it's classified as t-shirt top. So this is it seems to be a multiple t-shirt, but at least the classifier thinks, at least the label of this picture is t-shirt top. Okay. So what we're going to do is actually we're going to use a pre-trained model that we build for the purpose of this lecture. I'm going to introduce the specificities of the model. Specifically, we can download a pickle file. So this is just going to be a dictionary that contains the model weights. And this is a very simple model. So here's a model we're going to use in this lecture. And we're going to walk through different ways of building those models, including the low-level NumPy that we used in the last lecture, as well as some of the TVM's abstraction on building this particular end-to-end model. So this is a two-layer neural network, and I'm going to walk you through some of the components of the model definition. So here's the graphical form, and it contains, well, depending on how you count it, you can normally it's called two-layer because it contains two linear layers. But other people might also say, I see 3 layers in here, or if you look at the individual operation being performed, it might be 5 operations if you separate the matrix multiplication and the bioset. So the way it works is that first of all, we're going to take a flattened vector. So this 78 here is just 28 times 784 is 28 times 28, which is the input image, flattened as a vector. We're going to pass it to a linear layer. And this linear layer is defined as the same linear layer that we commonly use in PyTorch and other frameworks. So it's defined as, for taking input, you are going to take a matrix vector product of W0 transpose, and then you are going to plus a B, which is we call biased in here. Okay, and if you want to draw it out, it's like if you have an input neurons in here, that's X, and you have now 784 here, and you are going to project it onto 128 dimensions, where each of the output neuron is connected to the input neuron, so it's a fully connected layer. And then we are going to add a bias in here to try to offset some of the computations. Okay, and after we do this, I'm going to pass it to a RELU layer, rectifier linear unit layer, and then a second linear layer in here. Okay, so this is a visualization of the computation we're going to perform. Normally, in a two-layer neural network, we will end with a softmax, right? That gives a probability prediction. So typically there will be a soft max layer in here. And this is actually how we train the neural network as well. So originally, the neural network does come with a softmax layer. However, for prediction purposes, actually, we don't have to include this layer because softmax just normalizes the predicted score to probability. If we want to just pick the maximum value, we can just skip the softmax step. And the only reason we do that is just to simplify this example, so that we can really write it down by hand and show how to run predictions. Okay, I'm going to pause a bit and making sure that everybody understands the content here. Remember that first of all, we have 1 by 128, so this is a batch 1 prediction. And then in the second layer, we are going to have a hidden layer of 128 passing by RELU, and we're going to project it into a 10-dimensional vector where each dimension corresponds to the score of how likely that this input image is going to be classified as a particular object. Okay. So the first thing we're going to do is we're going to build a NumPy-based implementation of this particular model. And the way you do that is as follows. So it's pretty straightforward. So effectively, what you do is you have input data X. You first feed it into a matrix multiplication that corresponds to this one. And then you plus a bias in here. So this line corresponds to this first linear layer. And then you are going to do a RELU operation here and a second linear operation in here. So effectively, this is a code that describes the end-to-end model execution. Of course, this is a very simple two-layer neural network, but at least in terms of this course, it's the first time we ever define something that really corresponds to a neural network. Okay, and the advantage is that you can really write it in hand. You can really see what's behind the thing without a lot of the wrapping behind. Okay, so now we define the model. What you can do is we can load the model parameters. In this case, this fashion evidence is just a dictionary of T to NumPy. So we are going to read it, and then we're going to call the function. So the way we call it is we pass in the input image, get reshaped to the flattened format. And then we're going to pass in the argument that corresponds to W0, first 0 bias, W1, and bias 1 here. into this function. And finally, it's going to give us the result. Remember that the result contains different values. I can try to print it out, the result in here. And if you look at this, you'll find that the maximum value in here is this value. And that means that the predict con is going to equal 0. And then we're going to get the class dictionaries that's predefined of this data set. And then you look up the class dictionary. Okay, and we can also print the predict con to see if it is really is 0 as we expected. And if we print it out, you'll find yes, indeed, predict con equals 0. And as a result, it predicts t-shirt top. So yay, this is the first time we ever built a model, and this model gives us the right prediction, at least for that t-shirt top. This is the t-shirt top. Okay, so here's the first NumPy implementation of the end-to-end model execution. So far, so good. Now, again, for the purpose of this course, we're not only interested in this high-level array executions. If you look at this code, right, each line corresponds to kind of a sequence of high-level array computation described by the NumPy API. Of course, this is the kind of fine way to implement end-to-end neural network, and most of the time we should do that. One thing that we're really interested in is what happens behind the scene. And again, in this case, behind the scene, the NumPy APIs calls into underlying array computation libraries, dispatches onto them, and usually the framework will also do things like allocating intermediate memories, trying to tie them together, and in other cases, people might try to run GPU execution. So one of the goals of this course is we want to really not only look at the high-level implementations, but we also want to look at what is really behind the scene and discuss what are the possible optimizations and transformation we can do behind the scene. As a result, just like last lecture, we're going to go through a low-level NumPy implementation of the same model. Okay, so the way low-level NumPy works is not only we are going to use, we are trying to avoid array functions and try to unpack array functions using for loops of NumPy. The second thing is we always try to allocate explicitly when possible. This also tries to help us to map onto the real-world low-level executions that might happen on the framework. Okay, so we have implemented the tensor primitive function in the last lecture using low-level NumPy. So hopefully you are familiar with that. I'm going to go through some of the code, but I'm not going to stay as close as last lecture. You might be familiar with those layers, right? So first layer, you have low-level NumPy linear 0. That's the first linear layer where we do matrix multiplication in here. And the formula, remember the formula is y equals x times w transpose. And if we write it out, this in our index form, effectively it means yij equals sigma over k x ik times wjk. Okay, and if you read this code, it corresponds to the matrix multiplication, everyone. And this line corresponds to the bias add, where b is a bias term in here. One thing to remember is that just like the convention in the last lecture, not only we are going to pass in the input of the lower level NumPy primitive functions, we're also going to pass output like z in here directly onto the function, as opposed to having the function explicitly allocate the output. The reason is that most of the low-level implementations try to avoid memory allocation as much as possible and try to delegate as much as possible of a memory management to the framework. And machine learning framework will be able to do optimization like tiling memory together and so on. So this is kind of a specific low-level conventions that reflects what's happening behind the scene in a lot of the ML frameworks. So here's a low-level first layer of linear, here's a RELU layer, and here's a second linear layer. One thing you might notice is that the first linear layer, second linear layer looks almost same with each other, except some of iteration one are different. This is one particular way of writing it. Of course, we can try to write a generic code that works for all the shapes. In other cases of ML compilation, it might be useful to specialize. So to specifically generate code for the particular shape of interest. And we are trying to directly write it down in a way that represents this kind of like a shape specialized case. Okay, so in this case, we have 3 low-level primitive functions that correspond to the first layer, the RELU layer, the second linear layer. After these 3 primitive functions, we'll have this low-level NumPy MLP code that tries to tie things together. So this also roughly resembles what a low-level system might execute end-to-end neural network model. What it will do is to try to allocate the intermediate memory. In this case, the intermediate memory contains LV0, LV1, and of course LV2 is the output memory that we're interested in. And then what it's going to do is going to first call low-level NumPy 0 by passing an input W bias 0 and LV0 as output. After we call this function, we will get the result in LV0. And then we're going to call low-level NumPy RELU 0 by passing LV0 and populating the result on LV1, and so on. So hopefully, if you go and read the code, you'll be understand that, hey, this is really a low-level implementation of the same 2-layer multi-layer perception that predicts the fashion MNIST model. Okay, so and we can try to run it, and this is a similar code that we take in a low-level NumPy code. You pass in the data, weights, first layer weights bias and second layer weights bias. You get a result. You try to use argmax to get a result, and then you will get the class prediction. And we can try to run the code in here. If you run it, you'll find that, hey, this is t-shirt top. So it seems like it gives us the right prediction again. Okay. So now we have introduced a low-level NumPy implementation of the end-to-end neural network executions. Next, we are going to come back onto the topic of abstractions for representing end-to-end models, and we're going to construct an equivalent model in TVMScript. Okay, so here is a TVMScript code that corresponds to the same model implementation. It's slightly long, so I'm going to scroll a bit. And then we're going to come back to the key elements. Remember that in the last lecture, we talked about primitive tensor functions, and hopefully those functions look familiar, and they correspond to the primitive tensor functions that implement the RELU linear layer and the second layer linear layer. And if you are less familiar with it, try to take a look at the lecture notes of the last lecture that will contain the explanation of the tensor function. The main topic of interest, though, is that we have this additional function called r function that corresponds to a function that assembles those primitive functions together and really assembles the end-to-end neural network. Now we're going to take a closer look, particularly at this r function. So one thing that might be helpful is for us to take a look at both the r function and low-level NumPy function side by side. In this case, we can find that there's kind of like a almost one-to-one correspondence between the low-level NumPy function and the r function, which is a relax function. So relax is another abstraction in TVM that helps us to be able to compose up those higher level model computations by calling into those primitive tensor functions. So if you look at the figure here, you will find that there's correspondence, right? So LV0 in here correspond to the executions on linear 0. LV1 correspond to execution on the linear RELU layer, and the out correspond to executions of linear 1. So there's really a direct correspondence between the two. Now let's try to dive deeper onto the elements of the relax function so that we can look into some of the concepts in here. So first of all, besides the code view, it's actually very helpful to draw out the computational graph. So this is more like a graphical view for us to look into what's going on, right? And we have this figure in the beginning of a lecture. We have never explained what actually we have this figure in the past few lectures as well. We have never explained what they mean, but hopefully a lot of them look self-evident, right? So this is a view called computational graph. And if you are working on PyTorch or TensorFlow, this is the the mechanism behind the thing that drives all the computations in deep learning frameworks. Specifically, each of the node, the box here of a computational graph, correspond to a tensor function or tensor operation or primitive tensor operation that takes in some inputs and outputs output tensor. And in this case, you will find that we can find direct correspondence of each of the output to the variables in here. And each of the operations like linear, RELU, and linear can expand onto each of the lines in the relax function calls. So each of the line actually corresponds to one node in this computational graph. The interesting property of a computational graph is that this graph view really helps us to visualize what's going on in the model, right? So you will not only visualize what are the operations that we're going to perform on the model, it also visualizes the input-output dependency. So for example, it means we can see that clearly this particular operation takes in W0, B0, and X as inputs, and outputs LV0 that feeds into RELU layer. So the edges of computational graph really specifies the dependencies and how data flows from one operation onto another. As a result, in computer architecture and compilers, this graph is also normally called data flow graph, because it shows how data flows from one operation to another. Okay, so this is like one very useful view. And computational graph is also the most well-known abstractions in machine learning compilation, as well as machine learning framework. So you might already learn about this concept in other classes as well. And usually in the following lectures, we might interchangeably use the term computational graphs and relax function, in a sense that relax function can be viewed as a way to represent the computational graph. Okay, so one of the special things that you might notice though is that in this computational graph that we presented just before, you will find that there are some special construct here, specifically this called tier construct, which is slightly different from possible computational graphs that you might have seen before. So in this case, called tier takes in a few arguments, right? You have linear, which is the name of a lower level tensor primitive functions. We have a list of, actually, if you read carefully, you'll find that it corresponds to a list of inputs to these operations. These correspond to the shape of the output from this operation, and this corresponds to the data type of the output operations. Okay, so why do we have this called TIR construct or called tier construct? This is because it's a way for us to be able to connect the computational graph operations with the low-level primitive function. So to explain what does it mean, let's try to review actually a Numpy implementation of this called tier function. So effectively, this called tier function can be explained by this implementation. So in here, if we try to in verbal language talk about what does called tier mean, effectively what it means is it will take a function that have a quite special calling convention. So if we look at the functions we have, you'll find that most of the low-level function arguments looks like this. You have inputs, and then you have output that follows the input. So instead of directly returning the output, the lower level primitive function usually expects us to be able to pass in the input and then pass output together, pre-allocated output onto the function. This is a kind of special style of calling functions, and in a lot of cases, it's called destination passing, which means that we are passing the destination onto the function itself. So why do most low-level functions follow this convention? The reason is that, again, we mentioned it before, right? We want to be able to avoid explicit memory allocation as much as possible and let higher level framework execution to be able to handle those, so that low level implementation just focused on really getting the computation right instead of thinking about how I'm going to allocate and manage my memory. So as a result, a lot of the low level library functions kind of sits in this form where you have explicit input and explicit output. So having this destination parsing style, on the other hand, from a high-level computational graph point of view, we really want to be able to get a computational graph node that looks like this, right? So you have input, and you have output. So that, from a computational graph point of view, we really want to be able to have an operation that takes the input and directly return the output. So how do we convert a destination parsing style to an operation computational graph? This is the implementation, and it's quite straightforward. So what we do is we're going to first, for taking an input shape here and d type, we're going to first allocate a result, and we're going to call the prime function, which get passing as first argument, by unpacking the inputs and result together. So if you have not used this before in Python, effectively this means prime function. If I have my inputs list as x and y, effectively it will call the prime function with argument x, y, and the result. Okay, so it's going to unpack the input list and call it. And now if you compare this to this implementation, if you expand it out, you'll find that effectively it means I'm going to do result equals allocation, the corresponding shape, and d type. After allocations, I'm going to call the function with x, w0, b0 result, and then I'm going to return result as my final result of the argument. So effectively, I try to wrap the lower level primitive function that's destination parsing style onto a computational graph style operations that directly returns the result. Okay. Hopefully you understand what call here means. And this is actually a very interesting concept that allows us to be able to embed those low level calls directly onto computational graph. So, if you come and review the original Numpy implementation like this one, you'll find that this lower level Numpy implementation does not follow the style, right? It still have explicit allocations and calls. So why do we need to introduce call here as opposed to directly try to find something that try to represent this sequence operation? Well, we can try that. What you'll find is that we can have a possible failed attempt. So don't really do this, but there's one attempt that we can do to take this code and directly try to turn it into a graphical form where each of the nodes correspond to a function and the arrows correspond to the function inputs. And you'll find that it doesn't look really right? Although in reality, we're expecting execution like I'm going to execute this one and this one and this one. But from the graphical point of view, if you just look at the argument dependencies, there's not really a topological order between this first and next operation. Okay, so the reason is that actually, because we are performing allocations, and this lower level primitive function directly writes onto the allocated memory, this piece of code no longer is pure, or from a technical term is no longer side effect free. As a result, the computations no longer enjoys the nice computational property that computational graph abstraction enjoys. So most of the computational graph abstraction will expect each of the function node that it calls will directly only reads from its input and only returns its output without writing onto any of the inputs. And it wouldn't try to increment secret global variables that sit somewhere. So it's completely contained on that particular operation. And that brings a lot of benefit. For example, we can take a computational graph and try to directly traverse it in topological order, reorder it, or if there are parallel passes in a computational graph, like if there are if there's the operations like this, I would be able to parallelize this operation together without any problem if this is the computational graph form. However, requirement of a computational graph form is that each of those operations do not contain side effects. So they should not be able to write onto any of the input argument they have. Okay, so if we have our programs in this kind of lower level form that have explicit writings onto those allocated memory, then we can no longer have a computational graph that enjoys such properties. Of course, one idea is let's try to enhance this abstraction. Let's say maybe we want to, for each of our operations, we want to introduce the read and write relations, but that kind of defeats the real purpose in a sense that that's a more complete abstraction. So we will need to rethink how we're going to rewrite some of the transformations that are associated with that abstraction. Okay. So instead, what CoreTier help us is try to bring it back, right? Try to bring a primitive tensor function that explicitly expects destination passing back onto a computational graph form that is pure or side effect free. Okay. And by doing that, we can also, now we have this NumPy version of CoreTier, we can also, try to rewrite our lower level NumPy function using this, right? So here's an implementation that looks exactly like what we had on the relax function that, except that we're going to call into a lower level NumPy code in this case. And if we go and execute on this, you'll find actually, this lower level NumPy code with CoreTier also executes correctly. Right? So one thing that I want to mention is that, this lower level NumPy implementation of CoreTier is just a way for us to demonstrate the semantics of, what is the expected behavior of CoreTier construct in relax. In reality, we are going to build things onto low-level executions. Of course, the low-level execution is still going to contain memory allocations and other operations. However, when we are doing some of the higher-level transformations, for example, sometimes we might want to take two operators and fuse them together, or other transformations that decides what things can be parallelized, computational graph abstraction is really useful. So we want to stay in computational graph as much as possible. And that's why we are going to introduce and use CoreTier in this relax code. Another construct that you might realize by reading the code is that there's a r.dataflow block construct in this function. This also connects back to the computational graph concept we talked about before. Remember that, ideally we want everything to be in a computational graph form where each of our operations kind of, you can represent as a node of computations that reads some input and directly returns the output so that we can connect them onto a direct acyclic graph. But of course, during the MLC transformations, we can get to a possible state where we might need to introduce some of the side effect operations such as reading from file, generating random variables, or random variable generation, depending on how you implement it, it can be side effect free, but sometimes it might contain side effect. Or, in certain cases, maybe simply do explicit allocation. So in this case, we will need a way to be able to mark the region. So the idea is that although we cannot make the entire computation in a computational graph form, we want to mark regions where they can be in computational graph form while trying to, for the rest of the regions, be more careful so that we do not treat them as computational graphs. So in this case, we might introduce data flow block as a way to mark the region of computational graph. So specifically, remember that computational graph is also called data flow graph. Right? So a data flow block kind of marks the region of a computational graph. So within this region, all the computations can be viewed as a computational graph. However, there are other operations outside data flow block that need to be executed in sequential order with respect to the data flow block. So in this particular program, we have two data flow blocks and one operation outside the data flow block that need to be sequentialized. So if we have operation outside data flow block, you can no longer treat them as a direct acyclic graph. You kind of need to execute them in order. Or you need to do more advanced read-write analysis, or in compilers term called alias analysis, to be able to decide whether or not you can try to reorder or parallelize certain operations. But within a data flow block like this one, you can still view it as a, for example, in this case, it's just a linear layer with x, w0, b0. You want to feed it onto the RELU layer, and then it outputs onto gv0. Right? So you can definitely view this particular part as a computational graph. And the second thing is that we also need to mark the boundary of the computational graph. So that's why we have the output mark that says that this gv0 can be seen by the other block. So in this case, for example, gv0 is being referenced by this particular computational block. The other variables like lv0 is an intermediate variable that wouldn't be seen by other computational blocks. So as a result, maybe in optimization, we might be able to rewrite them in certain ways in a more effective way. In most of our lectures, we are only going to look at computational graph optimization. So as a result, likely for a lot of cases, we are only going to see a model that contains a single data flow block. But it's always good to keep that in mind, in a sense that although computational graph is a very nice abstraction, we may not be able to represent everything in computational graph. So we kind of need to be able to mark the computational graph regions and only apply relevant transformations onto those regions to be just careful. And of course, if we know more advanced compilation analysis, we can try to do other things that goes beyond the computational graph. But just to be extra careful, don't treat that as a graph if that's the case. Okay. So if you are a bit confused and about this, that's fine. In the one thing we can assume for the rest of the lectures is that we're going to only deal with one data flow block, which effectively means that the entire relax function corresponds to a single computational graph. Okay, so at this point we've talked about again the one machine learning compilation abstraction about these end-to-end model executions that contains the following elements. We talk about the computational graph view. We talk about called tier construct that takes in the primitive tensor function, that's the destination path style, and turn them to computational graph node. We talk about data flow blocks that marks the boundaries of computational graph. Okay, moving next, what we're going to do is we're going to, so far we have just talked about, hey, here's the code and here's what the code means. Of course, one of the things we want to do is we want to be able to deploy things. So we want to be able to build a corresponding module and run it on the environment. In this case, we're just going to run on the same environment that we're going to be building. In the following lectures, we'll talk about how do we deploy onto other kind of hardware. So to begin with, we're going to again use the script function to review the input a bit. It's a bit long, but remember the main thing that we care about is this main function that have a call tail element. Of course, the rest of element is also important. We've talked about in the last lecture, and we'll still be able to use the transformations that we taught in last lecture to change from the linear 0 and linear 1's implementation. Okay, so in order to turn this onto an executable module, what we'll do is we're going to call a build function. Actually, this build function and relax is still under development. So, the APIs may subject to change. On that hand, our main goal is to just get familiar with the overall machine learning compilation flow. So likely, the overall flow is still going to be the same. And one thing we can do is we can call relax vm.build in this case. That will give us a virtual machine executable that contains both execution module that runs this overall computation graph executions, as well as the compiled libraries that represents those primitive tensor functions. Okay. So once we build it, what we can do is we can use it to initialize the virtual machine. In this case, want to say that where do we want to store the intermediate computations? In this case, we are building a CPU module. And then we're also going to generate data in TVM's ND array. So data ND is input data that takes the input and convert it into TVM ND array. And we're also going to convert some of these multi-layer perceptual weights onto a dictionary. Okay. Once we do that, we can run the prediction. So remember, if you look at the function, it's a main function that contains the list of arguments of all the weights and bias. What we're going to do is we're going to call this main function with data and the list of parameters. It's going to give us the final prediction. If you read this prediction, you will find that the value is 12.3974747, same as the previous Numpy implementation, if you remember correctly. And we'll be able to confirm that in this case, this is a t-shirt top. Okay. So you'll find that actually we will be able to take an IRModule, in this case, that contains both the relax function that describes how do we assemble together the primitive tensor functions, as well as the primitive tensor function themselves to form an end-to-end execution. So if you look at this function, actually these two elements both are important. Right? We have this global assembly graph execution function that calls on to each of the primitive tensor functions, and when I call into this one, it actually invokes this particular implementation that runs that linear layer. Okay, so the key element of end-to-end executions contains those two parts, right? You have a high-level execution, which we usually call computation graph part, as well as a primitive tensor function part that supports all the libraries. Of course, one question that somebody might ask is, right now we are implementing almost all these primitive tensor functions in TVM and in TensorFlow. Right? In certain cases, one might say that, hey, I have a library implementation like CUDN or other implementation that's already in place, and would just like to call into those libraries instead of trying to call into a tier implementation. Effectively, we want to be able to replace those functions by a library function implementation, and we're going to show how to do that. So in this case, this is an alternative relax module that calls on to 3 library functions. So one thing that you'll find is that instead of calling into a function within the module, it's calling to, we are using strings in here. So inside the IRModule parsing, what happens is that these strings will be interpreted what we call an external function. And in this case, the name doesn't matter. We're just picking arbitrary names. Environment.linear means that it's just convention we use. You can pick another string. But the idea is that we are expecting the target execution runtime to contain those functions, like environment linear, environment RELU, that implements the corresponding operators. Okay, so in here, this r.callTier linear effectively means that we're going to call a function that hopefully is already in the environment, which is in the destination passing convention that we're expecting, and we're going to get a result. Okay, of course, we cannot directly execute it because we don't have those functions on our environment. So normally what we do is we want to go and register those functions. So in here, we're going to register 2 functions, the environment linear function and environment RELU function, onto a TVM execution environment. And this is the implementation of these 2 functions. So one thing that we're doing here is actually we are not implementing them, but we're just piggyback the implementation onto a PyTorch's implementation. So let me try to walk you through the code and show you what it means. So specifically, Torch and many machine learning frameworks have this function called from_DLPack. So DLPack is a standard exchange protocol. What it does is that it takes X, which is TVM and the array, that contains certain piece of memories, that contains data in here, and we're trying to convert it onto a Torch tensor by trying to exchange the data. So effectively, it's a Torch tensor that points to the same piece of memory. So this is very important in the sense that the DLPack is a way for different machine learning frameworks to exchange the tensor data structure without having to invoke copies. So effectively in here, the output Torch points to the same piece of memory as out in here. Okay, so if we are invoking PyTorch operations in here, we are mutating the original TVM and the array. So DLPack is actually a quite interesting initiative that involves many frameworks and friends, and I'm also one of those folks. and it's now part of the Array API standard. That means that it's going to be supported by Numpy, PyTorch, TVM, and a lot of other machine learning frameworks. So you will be able to make use of this and be able to leverage a lot of implementation from different libraries to implement your machine learning operation. Another thing that's useful is that if you're interested in building new libraries, you will also implement your operation and try to have an interface towards the OPAC. That means that other libraries like PyTorch and TensorFlow and TVM will be able to directly take benefit of your library as well. So after we convert those onto torch function that shares the same piece of memory, we're just going to call matrix multiplication, transpose, and add that implements the matrix multiplication bias in this case. One thing to remember is that, again, arguments in here follows a destination passing convention. So not only we passing the inputs, we also passing the outputs in here. And here's a RELU implementation here. Okay, so this two function registers an implementation using PyTorch in the environment in TVM. Now we have those functions ready. Actually, we will be able to grab them from the environment, directly invoke them. But of course, the built-in module will also be able to run them. And so what we do is we can build my module with kernel function call, run it by passing the same list of arguments. You get the same prediction. So for demonstration purposes, we are registering those environment functions in Python environment. In practice, for example, if I'm deploying to an embedded environment, of course, we cannot expect there will be Python. Right? So there are many ways for us to register those environment functions onto the runtime system, as long as they follow the same convention of input and output. And in TVM, there are languages like C++ and other native languages, Java and other languages that allows us to register those environment functions. And we're going to visit them in future lectures as well. So this is just an illustration example of how we might be able to interrogate our library functions onto those runtime environment and leverage them in Relax. Of course, in practice, you might see we have example that invokes an environment function, and we have another example that that directly calls into tier. Right? So in practice, we can have a mixture of both. For example, in this case, we have this function that directly calls to a tier function in here, and then the rest of the functions call to the environment functions. This is totally fine. We'll be able to build IRModule that effectively first call to this linear function, and then call to other library functions. And this is also very common in development, because in certain cases, maybe you want to try to study cases like, hey, for this particular operator in my MLC process, I'm interested in manually optimize it and see what are the possibilities. So in that case, I'm going to replace it with an environment function, and I'm going to manually optimize it and see, how it goes. If it works well, maybe, we want to bring it back to compilation solutions as well, right? So having the ability to be able to switch between those compilation and library implementation is really important. And as a result, we want to be able to support this kind of mixture. And again, if you try to build and run, you'll find that in this case, it actually gives you the same result. Okay. Up until now, we have built those end-to-end model functions with all the input arguments and parameters, right? You can imagine that. What if I have a 100-layer neural network? Then this parameter list is going to get very, very long, and it's not too convenient to do that. So there are approaches for us to be able to bind those model parameters onto the function themselves as constant. So here's an example that takes in the IRModule in here. In this case, we're taking model mixture and bind the main function with this ND parameter. So what this bind parameter tries to do is that it will try to look up the dictionaries and look at the function names. So in this dictionary, actually we have, you can find that there are W0, W1, B0, W1, B1, and that dictionary contains strings like W0, really the weights of W0, and so on. We're going to, basically that function is going to match the parameter name onto this name and trying to bind the constant onto the corresponding function. And we can run that, and if you look at the result, you'll find that now this main function only contains a single argument, and there are other things like meta constants. So this is what we call a meta array that stores the metadata parameter, in this case is metadata, of this entire IR module. We are not printing out the IR metadata because the weights can be very big, but effectively, it allows us to have a mechanism to store the data onto the meta dictionary. And this meta dictionary, although it's not printed out, is part of IR module. So we'll be able to compile it, and the resulting module will contain the corresponding constant in this case. So if we go and build this, you'll find that when we invoke the new main, right, because in this case, the new main only contains a single input in here. So we just need to pass in a single input, and the parameters already binded in. Again, t-shirt.top. Hopefully the fashion MNIST is the fun data set, and we are getting the same prediction result. And this is a much more friendly interface, right? You get input, you get output, the parameters embedded in the model. It's also very helpful to do that because in certain optimizations, we might want to be able to write certain parameters like change the layout and so on. We are going to talk about that in the future lectures, but this is one way for us to be able to transform our module a bit to be able to bind the constants onto the module. Okay, so far so good. We're getting close to the end of lecture. What we did today is we talk about several ways, I think 4 or 5 ways maybe, trying to, how do we go and build a low-level detailed abstraction implementation for an end-to-end neural network model. Of course, it's very simple, right? It's only 2-layer perception models, but hopefully you get all the details behind the scene of what machine learning compilation or machine learning framework might do executing that low-level models. And one thing that we notice is that a lot of the discussions come back to the discussion of abstraction and implementation, right? In a lot of cases, we are talking about what are the possible ways for us to represent end-to-end model execution. In this case, we have IRModule that contains the computational graph part and calls onto either a TensorFlow function or a library function. Both follows the destination path and style. Another thing that you realize is that although the implementation of TensorIR and the library might be different, they follow the same interface convention of inputs and output. And as long as they follow the same interface convention, you can use callter to call both of them without modifying the other side of the code. This is actually the power of abstraction interface, right? You define a clear interface that allows us to interact with the computational graph. And as long as the interface is settled down, you don't need to worry about the implementation details. Another thing is that we may use different ways to represent computation at different stages of MLC process. For example, it might be useful to start with a higher level computational graph. In a lot of cases, it doesn't even necessarily have to correspond to a called tier function. We're going to talk about some of the higher level operations in the future lectures. And at certain stages, we're going to say, hey, I really want to change this to call onto my favorite library. I really want to change it to my call onto a tier function. Then we're going to write those calls onto call those functions. Right? So again, the MLC process is about representing the programs in different possible ways and effectively doing transformations among them so that we are getting optimized program. And today's lecture is really about a way for us to talk about what are different ways to represent it. Right? We can certainly think about ways we can transform it as well. For example, in the last lecture, we talked about how we can transform a TensorIR function. One thing you can try to do is you can try to take the model mixture, take that linear layer, and use the schedule API to transform that particular linear zero function onto a different implementation and see, how does this end-to-end execution performance difference, right? So that's one possible way of transforming it. In other cases, we might want to be able to transform high-level model executions onto a mixture of library and function calls. So today, it really kind of established the overall framework that we're going to use for future lectures. In the future lectures, we're going to focus more on what are the possible transformations we can do that gets us better performance and so on. But really, everything centered around IRModule that contains a collection of tensor functions and transformations among tensor functions. Okay, so that's the end of today's lecture. And here's a summary that you can take a look. We're going to post the notebook onto the website. And in a few days, hopefully we'll also post some of our company exercise that helps you to get familiar with the concept. Thank you for coming to today's lecture.